there are times, suppose this is the trajectory of a particle, right? And this is an instantaneous location of the particle. This is an instantaneous location at a certain instant of time, t. This is the position vector of the particle as seen by the origin. This is the position vector of the particle as seen by the origin. Sometimes what is important for us in certain physical situations, to understand how this position vector is reorienting itself. Sometimes it becomes important for us to understand how it is reorienting itself. Orientation is about an angle. Orientation is about an angle. And an angle will be measured with respect to a reference line. An angle is measured with respect to a reference line. I can choose to call my x-axis a reference line. I can choose to call my x-axis a reference line. Then this angle theta will be a function of time measured with respect to the reference line. This theta would be a function of time, and rate of change of theta with respect to time, rate of change of theta with respect to time is called the angular velocity of the particle. Is called the angular velocity of the particle, and is commonly designated by omega. Is commonly designated by omega, and it is measured in radians per second. Radians per second. This d theta is change in angle, which is radians. Dt is change in time, which is seconds. So radians per second is a commonly used unit of angular velocity. Angular velocity. Suppose this theta varies as t squared plus t cube plus 1 as a function of time, then angular velocity of the particle at any given instant of time would be given by d theta dt, which is 2t plus 3t squared, would be the angular velocity at any given instant of time t. You can plug in t equal to 1 and you get angular velocity at t equal to 1. You can plug in t equal to 2, you get angular velocity at t equal to 2, and so on and so forth.